Morning, everyone, and thank you for joining us today for that webinar on accelerating naval design innovation with the SimCenter tools. My name is Cyril Jacks, and today I'm going to introduce our company, May HTT. So I'm a pre-sales engineer at May HTT. I'll start by introducing Maya before passing it on to Siemens, who will introduce themselves and take you through some of the marine industry challenges before talking about a few customer success stories. Then Seabird, our customer Seabird, will introduce themselves and let us know how they're leveraging the SimCenter tools on a day-to-day basis. My colleague Darius and myself will then take over for a deep dive on the technical tools, SimCenter Stars CM Plus on the 3D CFD side, and SimCenter AimSim on the 1D system simulation side. There'll be a few key takeaways at the end of the session, including an advertisement on our follow-up event, which will happen next month. So stay tuned until the end of the session if you want to know what's happening. Then we'll wrap up with a 10-minute Q&A session. So if you have any questions, please post them in the question section in GoTo, and then we'll be able to address them at the end of the webinar. So very briefly, who are we? May HTT, we are a 250 people company. We're based in the US, UK, Canada, and France. We're a global Siemens partner, and we've actually been recognized by Siemens for our simulation expertise. We do operate in 3 different areas. First one is that we are a VAR, a value-added reseller of Siemens. So we do resell the entire Siemens portfolio, covering PLM, CAD, and simulation tools. We do also provide consultancy services for our customers, whether it's from a training, a mentoring point of view to help you get up to speed and leverage the tools in the best way possible, or we can also realize full-on projects with you if you actually want us to do that. And last but not least, we're also an R&D center for Siemens. So we do co-develop and offer some of the modules that are being embedded within the SimCenter portfolio, including space systems thermal, FE model correlation, and quite a few of them. Right, on that, pass it to you, Abdul, to introduce yourself and Siemens.
Thanks, Cyril. Hello, everyone. My name is Abdul Ludi. I'm responsible for portfolio development across Europe, Middle East, and Africa. I'd like to take a brief moment to explain who we are as a company. Siemens is a global technology company, recognized as the world market leader in industrial automation and software. It is also the largest manufacturing company in Europe, with over 300,000 employees supporting our customers across the 5 continents. This year, Siemens was ranked in the top 10 list of the Time World Best Companies of 2024. Siemens has a rich history. It was founded in 1847 in Berlin, Germany, by Werner von Siemens. Today, the company operates across several strategic sectors like smart infrastructure, energy, mobility, health, and digital industry software, where we are based. Our mission within this division is to help companies drive innovation and enhance competitiveness through digital transformation, i.e. everything from design to manufacturing and production. The Digital Industries division comprises of multiple subdivisions, as you can see on the slide: software, factory automation, motion control, manufacturing process-related automation, and finally the services that offers our customers deep industrial expertise. The Digital Software division was established in 2007 with the acquisition of Unigraphics, or UGS. Today, it serves as the backbone of our NX shipbuilding design software. Since then, Siemens has invested over $10 billion in acquiring several innovative companies, such as Seeded Upco, which offers our flagship CFD solution, and Mentor Graphics for our integrated circuit design offering, all of which are key components of Siemens Xcelerator, which is a digital platform comprised of integrated solutions. The SimCenter portfolio is a critical component of this, which will be explained shortly. Siemens is committed to investing in cutting-edge technologies to keep our customers at the forefront of their industry. In line with this commitment, Siemens announced yesterday it plans to acquire Altair Engineering. This acquisition will position Siemens to offer the world's most comprehensive AI-powered design and simulation portfolio. With that brief intro, I'm pleased to introduce our next guest, Dr. Dimitri, who will talk about the market challenge and how Siemens is helping to meet those challenges. Dimitri, over to you.
Thank you very much, Abdul. Yes, my name is Dimitri, and I'm a Marine Director at Siemens Digital Industry Software. So it's a global role, and I'm overseeing the global maritime portfolio within Siemens. So I would like to share a few slides, if I can. For some reason it doesn't work. Let me see what I can do this way. Yes. So I would like to say a few words about the market trends and also the challenges of maritime industry. So the first thing is about the global challenge that we experience in the maritime business. So in July 2023, International Maritime Organization, which is the special agency of United Nations, committed to a new strategy. And according to this strategy, by 2050, so we have to make the entire global maritime industry zero emissions. So it's quite a significant technological change, because obviously, you know, the scaling up and using these new technologies for the entire global industry, it's not an easy task. So just to illustrate this, for instance, if you ask yourself, so how many vessels are actually sailing on the planet at the moment? So the answer would be it's about 100,000 vessels for the gross more than 100 gross tons, and about 50,000 vessels with more than 1,000 gross tons. And at the moment, only a few of those vessels, they're actually zero emission. So it means in the next 20-25 years, it's going to be quite an interesting and challenging process, you know, to completely change the future of maritime business and update all these existing vessels and do something about this. So as you're probably aware, so the general process of the shipbuilding, so it starts with the inquiry, and there are quite a significant blocks which go all the way to the in-service support. And because the digital technologies in the shipbuilding were introduced quite some time ago, so now for almost every part of this process, for the initial design, for the contract, for the detailed design, so there are some sort of packages or software software packages to simplify the this kind of process. And obviously within the Siemens portfolio, so we have all the tools which is actually needed for the entire process, for the PLM solutions, for the global kind of overseeing the management processes, and also for the detailed design and simulation bit. So in that sense, Siemens is actually it's in a very good position, so we can cover all the blocks of this process. But probably the most important bit is actually to have the seamless integration between those components. So it's not like pieces of software from the different vendors, and you might be challenging, you know, to move the file from one piece to another. But it's kind of the integrated, full integrated approach. So in this, if we just rearrange the same image in this block, so obviously there are like a few main steps, which is requirement, concept, design, manufacturing, and operations. And in simulation part, so we mainly focus on the concept and design. So that's exactly the area of expertise which could be used with the Siemens simulation portfolio. This portfolio, so is specifically part of the Siemens solutions called SimCenter, and is mainly focused on the simulation and test. But in that case, so it could be fluid dynamics, so computational fluid dynamics simulation, it could be structural, it could be thermal, it could be acoustic. So all this part of the simulation process could be united in the SimCenter. So in that sense, we would like to highlight a few main blocks of this portfolio. So why it's important to make the simulation process, the part of the shipbuilding process. So the first one is obviously modeling the complexity, because obviously at the moment the ships, they are not simple structures. So there are a lot of things happening on the vessel. So it could be some sort of, the hydrodynamic side, structural elements and so on. So it would be nice to have the opportunity to have this, to model this complexity in full. Also, the second bit is about exploring the possibilities. So this is quite an interesting option, for instance, for the optimization process. So if you would like to have the optimization space and just try to find the best possible answer or the best possible solution, either in hydrodynamic side or structural response, and so on. Another critical bit, it's about the, being able to run your simulation in a reasonable time frame, because obviously before, simulation could take days or obviously even sometimes a week, depending on the complexity. But for the design process, it would be nice to have those simulations be delivered in a reasonable amount of time. So that's why we have a quite significant focus on the making our simulation robust and fast. So that's why now we're quite keen to show this graph, showing that the general time frame for running the simulation is actually reduced quite significantly. And this is definitely will help the engineers to run the cases in a realistic time frame. And the last, but also very important bit is about being integrated. So as I mentioned before, there is opportunity to, let's say, to design or like to build the first geometry, initial geometry, for instance, in NX, and then use kind of this file over there, like all portfolio of Siemens products. So in that case, you don't have this headache of transforming or converting the files from one file format to another. So it's kind of they all connected and integrated, and obviously it's made the simulation and the entire process in an easier way. So that's in a nutshell what I wanted to say about the marine trend, and would also like to share a few customer success stories. So one is actually DNV, the Norwegian Classification Society. So they are very good clients of us, and they use Star CCM Plus to optimize the hull form. And as they reported in one of their projects, so they achieved 36% of improvement in energy efficiency. So this is a quite significant gain. And obviously, so if you just convert this to the financial, so it's quite significant, saving about 3 million per year per vessel. So it's one of the opportunities for the designers and owner to improve their designs. The second test case is from Wärtsilä. So they had a similar approach using Star CCM Plus, but their focus was not specifically on the hull form, but also the integration and let's say some sort of collaboration, or not even collaboration, interaction. So that's the word I was looking for. Interaction between the hull form and the propeller. And by doing that, so it's very important to find the right hull form and propeller together. So it's to run the to get the very good wake fraction. So or like wave behind the vessel, in order to make to make sure the propeller is operated in a favorable condition. So in that case, obviously their focus was not only specifically the hull form, but also the integration, the scour form, and running the simulation together with the propeller. And finally, one of the test cases is Becker Marine System. So they are very famous brand and company to design Mervis duct. So it's a special energy-saving device which installed in front of the propeller, and it can make the flow coming to propeller a bit more uniform. And by doing that, you can specifically make like significant saving in the propulsion system. So as reported by Becker Marine, so they can actually achieve quite significant saving, about 0.5 million per vessel for the fuel. So it's also quite significant, taking into account it's quite a small installation time for this unit. So obviously we could share quite a lot of success story in the future, but we're quite limited of time. So that's why I would like to focus on these 3 success stories that I mentioned before. And I would like to give floor to our next speaker, which is Seabird. And yeah, if you could share your presentation, that would be perfect. Yes, we can see the presentation. So thank you very much. The floor is yours.
Thank you, Dimitri. Hi, everyone. I'm Samuel Moss. I'm the lead structural engineer here at Seabird Technologies. I have over 10 years experience in developing vehicle body structures in the automotive industry, and now I'm applying my expertise to innovate in the marine sector.
Hi everyone, I'm Ishan and I'm a thermofluids engineer here at Seabird. My responsibility is to run CFD simulations to analyze and improve the performance of our products. My main expertise lies in using parametric geometries with simulation and automation tools to develop efficient workflows for design development.
So I'm going to start off by taking you through who Seabird are, what we do, and then Ishan will fill in with the technical elements. So what do we do? Seabird Technologies is an early stage marine tech startup. Our aim and focus is developing electric propulsion systems for leisure and commercial vessels across the marine industry. And this covers many system types, such as electric motors, power management systems, battery systems and control systems, with more to come in the future. So how are we doing this? Well, currently most electric propulsion systems on the market are retrofit solutions to the internal combustion engines, which have been around for decades. At Seabird, we're taking a clean sheet approach, developing everything from the ground up, and we hope this will enable us to create truly innovative products that are optimized for their application. And we're calling this approach Electric 2.0. So Seabird started out by designing the electric foiling race boats called Racebird for the E1 race series, which has just concluded its first season with Team Brady winning the World Championship. The Racebird reaches speeds of 50 knots on tight courses in marinas and lakes around the world. And it utilizes our 150 kilowatt power unit alongside cutting edge foiling technology to deliver a highly efficient, high performance race boat. And on the next, and really the success of this project highlights and demonstrates our team's ability and capability to innovate. On the next slide, we have a little snippet for you of the Racebird in action. This is taken at a test site in Italy on Lake Maggiore.
I'm hoping that came through okay. Should have given you an idea of the speed at which the Racebirds perform. And it's our responsibility to make sure that the design can withstand those harsh conditions experienced during racing. In order to do so, we have to leverage state-of-the-art tools available to us. This outboard engine and foil system shown here is a critical component of the Racebird. Using StarCCM+, we were able to simulate its performance in a range of speeds and turning angles and establish worst cases. We can then take those worst cases and analyze them in more detail to feed into other disciplines, such as providing pressure maps for structural analysis. Iterating through that process has allowed us to develop robust design solutions without compromising on hydrodynamic performance.
Thanks, Ishan. Another way we're developing new technologies is through the various Innovate UK projects that we've won. These are partly funded by the UK government. As you can see on screen, we are working closely with many commercial and academic partners on a range of topics, such as Project Osprey, which is a UK-Germany bilateral project where we're working with Hacker Motors and the University of Cambridge in developing electric foiling propulsion systems. We have Project Spera, where we're developing smart digital tools for optimizing powertrains and wind-assisted ships with the likes of UCL and Scotline. And on the right-hand side there, you can see a image of one of Spera's concept vessels. And then finally, Project Optima, where our aim is to produce the most energy efficient, emission-free electric vessel on the market for leisure and commercial applications. That's working with the likes of Timebridge Propellers and Ultima Yachts, and you can see one of their vessels on the right-hand side there as well.
Optima is our longest running Innovate UK project, and given its focus on efficiency, has relied heavily on CFD simulations. For Optima, we have simulated a real-life vessel in full scale and been able to validate our results against sea trial data to a high level of accuracy. As you can imagine, a validated simulation has proved invaluable for the development of our project, ensuring that any design changes we make, we can say with confidence will perform on the vessel. Some improvements have already been made and are performing well. On the right-hand side, you can see an image from the underside of the vessel. In the top half, giving you a visualization of the wake, indicating the complexity of the simulations. You can also see a hydrofoil that we've placed below the central hull to try and further improve vessel resistance. Using StarCCM Plus's Design Manager, alongside its inbuilt parametric modeling tools, has allowed us to use this highly complex simulation for design purposes to optimize the foil's position and size. Aside from our external research projects, we also conduct a large amount of research internally to better improve and understand marine systems. This project aimed to develop the design, including the foils and hull foiling yacht, to improve the overall vessel efficiency through takeoff. StarCCM, as we've seen with Optima, is capable of accurately modeling vessels in full scale, and it can also capture the dynamics involved during takeoff and foiling. But at the same time, we're able to control wave conditions and wind speed that we can't do during sea trials. Being able to control where we have the complexity and where we want the simplicity is why it makes a great tool for research projects. So we talked about the Racebird and the research we're doing, and it's that racing expertise and technical insight that we're using to develop our very own line of commercial products. We're very excited to announce that we will be revealing our first concept product at METS in Amsterdam later this month. And it's what we believe to be the beginning of the next generation in electric systems for the marine industry. So feel free to follow us on social media using those links shown, and feel free also to reach out at the email address given. And if you're at METS, come and say hi, and you get to see our full-scale concept in person. Thank you.
Thank you, Jean-Samer. Take back over the screen. And yeah, so thank you. From there, I'll take over for a section on SimCenter StarCCM Plus. So we're going to see how you can leverage that tool to model from the simple hull resistance model to the complex maneuvering predictions. Some of it will probably echo what you've already seen from Ishan and Samer. So as you've understood, StarCCM Plus is our 3D CFD multiphysics tool, which means that you can model quite a wide range of applications. And if we focus on the marine industry, that does mean maneuvering, seakeeping, submarines, high-speed craft, multi-body interactions, etc., etc. There's a wide range of physics, as you can see on the right-hand side of the screen, which does allow you to model even more physics and even more applications in different industries, as you can imagine. If we focus back on the marine industry, we're going to talk about 4 different things here. The standard simulation workflow to model a marine simulation. So if some of you know CFD, I think, and you've used a commercial tool before, you'll be very familiar with that. Then how you can actually leverage the templating in StarCCM Plus to automate your workflows. Once you've automated it, you can go further and explore your design space and try and optimize and find better designs faster. And then the last point, but not the least, if for some reason you need increased fidelity, for design gateway or for validation and correlation purposes, we'll see how you can also do that in the tool. Right, so let's jump into the CFD workflow. So no surprise there. The first step is the CAD import. We support a wide range of CAD formats in StarCCM+. And from there, you have to clean your CAD to make it CFD ready. So you have to get rid of self-penetrating faces and make sure it's watertight, for example. Once you've done that, you can specify your mesh settings and generate it, check it, make sure it's of high quality. Then you can select your physics solver, your boundary conditions, and you're ready to submit and launch your calculation. The calculation is fully interactive in STAR, meaning that you can check for convergence and monitor your results as the run is happening. Then we arrive to the most important step of the process, which is the post-processing. So where us engineers actually earn our money, because you're supposed to have a look at the results, identify an area of improvement, you come back to the geometry, you make a change, and you rerun the simulation. So let's see in STAR how that fares. So here we are in the parts tab, where you essentially import your parts and you clean them. Then you define your mesh settings in the mesh operations here. So whether it's a surface mesh, a volume mesh, a boundary layer mesh, and you notice quite a few actually default controls to control the mesh sizes absolutely everywhere within your domain. So don't be scared by the amount of controls that you can see here. You actually only need to define them once, because they're defined in the operations tab, meaning that you can actually rerun them seamlessly once you've defined them. From there, you can very quickly create a scene which allows you to visualize the mesh that you've created. So you can potentially create a plane section and have a look at your geometric features, all flow features. And in this case, you can see a boundary layer mesh around our hull to make sure that we've captured that correctly. Then we move on to the physics solver. So everything happens in that window. So it's very easy to tick boxes and select your turbulence model. Is there going to be heat transfer or not? Is that going to be a steady state, a transient? Is that going to be a 2D or 3D case? We then move on to our regions tab, where we can specify our boundary conditions. So here we have a velocity, a pressure outlet, and a few walls for our geometries. Just before submitting our calculation, we're actually going to do our post-processing first, because the solution is interactive. So it makes sense to realize if something is going wrong at the start of the case, rather than running it fully and realize that you have to start from scratch again. And then once you've done that and completed your run, you can actually see there on screen a few capabilities in terms of post-processing for STAR, including streamlines, advanced rendering, ISO surfaces as well, which really gives you a fully comprehensive view of what's happening within your case. You may be presenting these results to some people who are not CFD experts, so you need to be able to make an impact visually and also pass on the message very easily. So that's what StarCCM+ is really good at as well. Right, there is one area of the process that we've not really covered so far, which is the pre-processing part of the process. And that process can be very tedious, especially in the marine industry, because most of our customers would receive a Rhino part coming from their suppliers, and this part is very often not the cleanest. Therefore, you have to spend a lot of time manually fixing all of that by yourself. In which case, what we've come up with at Siemens and MEA is the surface wrapper, which allows you to automate the geometry preparation. So let's see how you do that in STAR. You come back in your parts. This time you go into the repair surface tool, which is a pre-processing tool to check for errors in your geometry. In which case here we're checking and we're identifying self-penetrating faces, free edges, non-manifold edges, and vertices. And in which case we're going to create a new operation in our set of operations called surface wrapper, and we generate a wrap of our surface. Here we're comparing on the right-hand side the wrapped surface versus the original geometry on the left, and you can see that we've actually generated a very high quality surface on the right. We can then leverage the deviation distance fill function to actually check how far away the generated wrapped surface is from the original surface, and you can see that it's of very good quality. From there, we move back into our standard simulation workflow. So we generate our surface mesh to get these very high quality triangles. And then on top of that, obviously the volume mesh, and then you're ready to set up your boundary conditions and your physics solvers from there. So this is how we automate the workflow in terms of pre-processing the geometry as well. And then how do you actually save that in terms of a template. Every customer that's got StarCCM Plus has got the opportunity to create its own workflow and save it as a template and then distribute it across your organization. But there are certain templates that are already prepared by Siemens and available on the Support Center website. One of them is the virtual tow tank template, which is a template to run a hydrodynamic resistance simulation in flat water. So in here, you're going to get the resistance versus your speed, and this is how you're going to do it in the software. So you start by importing your geometry, so standard here. You will actually have it displayed on the graphics window on the right-hand side, so you can check for any errors. And then from there, there's only a few parameters that you have to enter. So the draught, for example, and the velocity of the vessel. You can also modify the parameters of the water, so the temperature, the density, etc. And from there, you just need to click Run. For those of you who know StarCCM Plus, you'll notice that we haven't run on the usual Run button. We've clicked on Simulation Operations. Simulation operations are a great way to automate your workflow because they allow you to define pre-processing activities, post-processing setup as well, and everything happens in the background. And as you can see, we just clicked on that button and the case is running converged, and you can see the post-processing views that we can obtain from such a template. And as I mentioned, you get obviously your resistance plot as well as the resulting motion of the ship. There is another template as well, which is called the Propeller Open Water template, which allows you to import your propeller this time in open water. And you have a few parameters to tweak. Once again, diameter, RPM, and using the Design Manager in StarCCM Plus, you can run a parametric study to get your propeller curves, which is obviously very important for propeller engineers. So here we're talking about thrust, torque, and efficiency, which are obtained very easily using that tool. Last but not least, we've got, so we're now back on the VTT template once again, but there's a new functionality which has been added this year, which does allow you to create a propeller, or at least implicitly using a virtual disk method. So in this case, we're not importing any geometry of propeller. We are creating and defining that pink cylinder that you can see on screen. And we're then importing a CSV file for our propeller curves, and there'll be a momentum source term induced in our case, which will replicate the impact of our propeller. And from there, we just run the template as usual, and we're getting our resistance curve, as you can see, which is slightly increased with the propeller, as you'd expect, because of the impact of the propeller on the flow. Moving ahead, you can go further, and so far I've just talked about flat water simulation. You can obviously simulate waves as well. So we've got initial conditions named VOF waves, which allow you to define linear or non-linear waves in your case. And you can also go further and do some maneuvering analysis by, for example, defining a trajectory, which would be, due to rudder or propeller effects. And that's what you can define in StarCCM Plus as well, if you wish. Moving on to design space exploration, there are two things here that I need to talk about. The Design Manager, I've talked about it already, where you can do parametric studies, and the Sherpa algorithm, which is our optimization algorithm embedded in StarCCM Plus. If we go back to our previous workflow, I mentioned that obviously a marine engineer is gonna, or any CFD engineer is gonna have a look at his results, come back, make a change to the geometry, and then rerun his case. You can forget about that with Sherpa. Sherpa is gonna have a look at your objectives, see what parameters you have, and is gonna find the better design for you based on the algorithm. So that greatly increases the speed at which you can find better designs. So if we have a look at how that looks in StarCCM Plus, and I think that was actually on Dimitri's slide earlier, so you may remember that view. You've got here the Design Manager, where we are running a parametric study using a simulation parameter, which is the wind direction. So we're running different angle of attacks. You can see that the view is fully interactive, so all the post-processing view update in real time. And so we can use 3 different parameters in the Design Manager: simulation parameter, mesh parameters if you want to run mesh independency study, and geometry parameters if you want to run a geometry optimization using Sherpa, for example. And that's what we're doing in the next slide. So here we are connecting NX, our CAD tool, with StarCCM Plus. in order to leverage the parameters and the geometry directly being transferred from NX, which does allow us to get a much more complex geometry parameterization, as you can see on screen. And here what we're going to do is that we're going to then use the Sherpa algorithm in the design manager to define two operating conditions and tell the algorithm to minimize the total resistance for a fully loaded operating condition and an empty ballast operating condition, which means that the algorithm actually has to find a good compromise between these two operating conditions, and that's exactly what is done in that case. So it's as simple as that. You define your objectives properly, you have your parameters in the case, Sherpa is doing the job for you. And that's what is found in the end. So you have the best design that has been generated at the top versus the baseline design at the bottom. If you look on the left, you can see that visually the wake has been reduced behind the hull. And on the right-hand side, you can also see that the wall shear stress has reduced on the hull, meaning there's been a decrease in friction, so a decrease in resistance. Moving on to the last section, if you want to actually increase fidelity for specific applications, as I mentioned, potentially a specific design gateway, certification activities, or a correlation activity or validation versus a prototype, we're not going to necessarily use the same physics model that we've used so far. We talked about optimization and running hundreds of cases potentially. If you consider an aerodynamic case, you're going to run a RANS simulation. That's not necessarily going to be the case if you want an increased fidelity. So in which case you can leverage LES and DES models available in StarCCM Plus to do that. You can also leverage some of our Lagrangian multi-phase models to track emissions and particles if that's of interest to you. One more set of capabilities that is in the tool is the multi-phase model that allows you to model cavitation. Cavitation is obviously a big concern for propeller engineers for three reasons. The first one being the performance, the second one being the durability and the structural aspect. We have a structural solver in StarCCM Plus as well that you can leverage, and using fluid structure interaction models, you can get the deformations and the constraints of your propeller due to cavitation or just the surrounding flow. And then obviously the third one is the noise generated by the propeller. We do have hydroacoustics model as well in StarCCM Plus, which allows you to get the noise generated by that propeller and obviously the noise propagation in your domain after. Right, so that sort of concludes everything that I had to say on the StarCCM Plus section. So we went from looking at how you actually simulate your workflow in StarCCM Plus, how you can then use the templates-driven approach in StarCCM Plus to automate it. And once you've automated your baseline as a template, you can then use design space exploration to go further. And obviously, we do have a wide range of applications and increased fidelity models if needed. Darius, I'll pass it to you on the AIMSIM side.
Okay, hello, thank you, Cyril. Can you hear me?
Yep.
Good, so I take it from here. As Cyril mentioned, my name is Darius. I'm Darius Piuro. I'm systems simulation specialist at Maya HTT. In this part of presentation, we will see how SimCenter AMISIM can help us with analysis of ship propulsion systems.
Sorry, Darius, I think you're muted.
Sorry for that, something is changed. Can you hear me now?
Yeah, we can hear you.
Okay, so SimCenter AMISIM is a 0D, 1D simulation tool, which has got about 6,500 off-the-shelf components models, if you like. And those components cover multi-domains, like multi-physics, for example, hydraulics, electrical, thermal, and so on. So what we use AMISIM for is that we build a system, and specific application might be like propulsion or HVAC or electrical system that is on board of the ship. So as you know, the ship is itself system of systems. And then once we've done this model build, we can analyze different performances, like we can size components, we can do what if benchmarking and so on. And generally speaking, MEC models can be run in real time. And what does it mean? It means that those models can be used for software development, like modeling the loop, hardware loop type of analysis, when we can link PLC sites to an MEC model representing the plant, and then we can virtually commission that PLC code. So this is how powerful MEC is. And as we will see later, we can actually leverage a CFD environment, in this case, Star System Plus, and use results of CFD simulations using MECSIM or link directly to CFD. Let's see on this simple example model, MEC model, how it looks like. So the blocks are intuitive. I suppose you can see right away that on the left we've got the ship, on the right we've got the weather conditions, so it's sea and wind. And around those two blocks, we actually build the other components. So moving from the ship, you can see there are 3 propellers that are powered by the electric motors. They are connected to the electrical grid. That on that same electrical grid, we've got the battery and 3 generators powered by internal combustion engines. So as you can see, this is kind of like hybrid propulsion system, when you can power the vessel from engines without the battery. You can power it from the battery, or you can power it from the battery and the engines. And this level of the model in MECSIM is let's say, performance-based. So we've got the performance tables for the engine, for the generators and electric motors, and you can plug them in and you see how the system performs, how much power is required, fuel consumption, and so on. But in MECSIM, we can also go into the one level deeper into the components design. So for example, if you know physics of the electric machine or the design of the engine, like piston, stroke, and so on, you can affect those parameters and see how they affect the whole system design. So this is very powerful tool for analyzing from the single component impact on the whole system. And in this specific application for ships, we've got here also sea routes. So we can have a specific particular sea route with a solution for a known ship or design ship with the propulsion systems of interest. And then you can analyze how will the ship behave across this sea route. And this slide is just to show you how we analyze the results from MECSIM. So it's mainly by plotting them. So it's plot. And on the top row, you can see that you've got the same information about fuel consumption and emissions, but one is expressed like the total fuel consumption and emissions over the trip, and the other one is versus time. So it's like cumulative. You can see that fuel consumption is rising in the trip for the ship. And then here we can see that International Marine Organization is giving some requests for the ship to meet 2 conditions. It has to be able to travel at 14 knots at calm water, and it also be capable of doing 4 knots at adverse weather conditions like Beaufort wind scale 7. So how do we make sure that our design meets those requirements? We can use something with my mouse. We can use MECSIM exactly for answering those questions. So we can size the propulsion system, and we can analyze it based on the simulation results. So on this simple model, we've got ship, propeller, and weather conditions, and we control the propeller speed. In this way, we control the vessel speed as well. So we make sure that this vessel is traveling at 14 knots, and we use the statistical hull resistance model here. And the outcome is that we need about 4.5 megawatt of power at the propeller. And you can see that with few clicks, we can change the weather conditions. So now we're going from calm water to the Beaufort 7 wind, and then we have to see how much power will our vessel require at 4 knots. So on this one, will be about 1 megawatt. So you can see that with just few clicks, we can analyze the sizings of the system, power demand. And if we know the candidate engine power curve, we can compare this power curve, which is red line here, to the actual simulation points for 4 knots and calm water and adverse conditions. So this will give us very quickly understanding whether these power systems will do. So we can take the right decisions at the very start of the project. So what we can do then, as the project advances, as what my colleague Cyril explained, that we can have a lot of iterations in the CFD environment, we'll have a lot of data coming out of this simulation tool. and you can bring them along to SimCenter MESIM. So in this model, you can see that we expanded the previous model by adding engine here. So we've got now engine performance maps that we can use for analysis of fuel consumption and emissions and all that important information. And we will do here something with a comparison between a statistical Hull model, which is built into MESIM, and how it will compare against that Hull model resistance coming from CFD. So you remember on one slide from Cyril, you can see that there was this speed versus resistance information. And we basically bring in this information to MESIM in form of this table. So you can see there are two columns. One is speed in knots, another one is resistance in newtons. And this is when we reuse the information generated by CFD environment within MESIM. So again, few clicks, and you've got those two information, I mean statistical Hull and more high fidelity information from CFD compared against each other. And also you can do much more studies. So for example, you got self-propulsion system resistance coming from CFD environment. You can plug in here as well. You can do some batch runs, benchmarking between different solutions. And again, very quickly on graphs, you can compare how those different resistance models are impacting the system performance. So you've seen how easy it is to combine CFD powerful information with quick simulations in MESIM. And that's not all. So what we can do also is we can go one step ahead, and then if you go to the high fidelity model in CFD environment of the ship, hull, and propeller, and all that which is done there, and very high fidelity model, very accurate model of the propulsion systems or any other system within the ship or in MESIM, you can link them together. So we're linking two simulation environments together by something which is called functional mockup interface. So this allows for two-way information exchange between two environments, and you can use it very effectively for holistic simulation of the ship. So as you can see on this animation, ship is going through some dynamic ways, and the dynamic ways will impact the power that propeller is exposed to. And that will propagate back to the engine, so we can understand how engine will be loaded, so torque load on the engine. And parallel to that, if you've got auxiliary systems and any other systems on the ship as well, you can then understand the full picture of the ship performance by running two tools in parallel. So in a quick summary here, you can see that it's simulation assists and helps the project from the very start of the project, so you don't have to wait for the project to advance. So you can take ahead of any information. We can use simulations to predict system performance based on our best knowledge or previous experience and so on. And then when the project advances, we can leverage on the fidelity of the models by using more accurate, more high fidelity data coming from CFD environment and bring them into MESIM. And then we can, if you want to link two tools together and run really high fidelity model of the ship from the holistic point of view. And I think this is all on my side, so I'll give it back now to Cyril.
Thank you, Darius. Thank you for that. Right, so we'll move on to the key takeaways and the conclusion of the webinar. And I know there was a lot covered today, so I hope by the end of that webinar you have understood that we offer quite a full suite of tools, both from the 1D side with MESIM and both from the 3D side with StarCCM Plus, to be able to create a full digital twin of your complete ship and propulsion system. This digital twin should give you an accurate and detailed representation of your hull, which would save you from creating prototypes and actually help you in terms of designing energy-saving technologies. It should also help you to predict ship fuel consumption and performance in any sea conditions, whilst you can even go further and run optimization in some cases when needed, in order to make sure you have a solution that complies fully with any guidelines or regulations out there. I did mention at the start of the meeting that the webinar, that we would have a follow-on event. So that's going to happen on the 26th of November. So save the date. It will be in London. It will be a free hands-on training workshop where you'll have the opportunity to try SimCenter StarCCM Plus in the presence of Siemens and Meya HTT experts that will help you and teach you how to use the tool. There's only a limited number of seats, so make sure you register your spot quite quickly. You should all receive a link by email at the end of the webinar. And actually, as I speak, my colleague Talia should have launched a poll in the webinar so that you can actually indicate your interest and secure your spot for that webinar. Right. Whilst you're answering the poll, I'll turn myself to the Q&A section. So we'll have approximately 10 minutes or less, depending on the number of questions. And yeah, let me have a look at the questions. So I see we have a few questions that that came in. The first one was, how difficult is it to adopt these tools? I guess that's a question, well, it could be a question for anyone, to be honest. So maybe if I'll start by answering, but then if you know, if Abdul, Ishan, Samuel, Dimitri, if you want to chip in, Darius, don't hesitate. So I think the adoption can be made in different ways. Obviously, if you have experts in-house, that's going to be easier for you to do it. But if you don't, we can help you by doing that. We, as I mentioned at the start, we offer services in the sense that we can help with doing a project, a baseline for you, and do some knowledge transfer, or we can do some training and mentoring as well to help you in this way. There's a second question that came in as well. AimSim and SimCenter allow propulsion systems to be included. Does it also include rudders and bow foils? To this extent, how do you cope with hydrofoils? That's mostly, well, on the AimSim side. I don't know, Darius, if you wanna take that one.
So on AimSim side, it would be like, can you hear me? Can you see me?
Yep.
On AimSim side, it would be when we model them from the point of view of the power required from the systems, if you like. So if you got that components in the design and you need to operate them, we can use AimSim to answer the questions like, you know, what would be the systems to operate them? Is it electric motor? Is it mechanical arrangement? Is it something else there? Controllability of that, so how smooth it moves, how quick it moves. So if it's, you know, controlled by electric motor, you can find out the performance characteristics of the electric motor which need to be there. So in this way, you can implement them in AimSim side. And on SimCenter StarCCM, I suppose you can answer, Cyril, how they affect the aerodynamics of the ship.
Yeah, I was going to answer from the rudder side. You can definitely import your geometry in there, and there's a few ways to model it. You could use what we call a sliding mesh or rigid body motion to do that, or you have also the overset mesh that can be used depending on how much your rudder is going to move in your case. In terms of foils, I don't know if Ish and Samuel, maybe you want to mention how you guys are doing it in-house, because I know you work on that.
Yeah, I think on the foiling side, it really depends on exactly what the problem is. So I think we talked about two situations. So either you're looking at isolated foils that are attached via a separate system, and you want to explore how that foil angle attack or position or sizing is going to affect the system. For that, as you said, Cyril, we typically use overset meshes separate from the main vessel to allow for flexibility in meshing, and it allows us to automate that design manager workflow a bit cleaner because it doesn't have to mesh each time the simulation runs. But in more complicated setups where there's a bit more interaction, we might just model it as part of the solid vessel. But in general, we try to design the simulation, like construct the simulation in a way that the foils and the boat's geometries are distinct representations, so that we can extract what their contribution is to overall resistance, overall forces, and that allows us to understand how much is the hull or the boat contributing to the flow condition and how much is the foil contributing.
Yeah, that makes sense. Thank you, Ishan. I've seen another question as well that came in, and it's also for you, Ishan and Samuel. how does Star CCM Plus handle high-speed crafts such as yours, especially in terms of numerical ventilation?
Yeah, this is actually something that I researched not too long ago, and it's a common problem that is still, from my understanding, present in a lot of the simulations. It's very easy risk to have. I'm aware that Siemens has its own VOS slip model, which is effectively a internal methodology for avoiding those numerical ventilation issues. And basically what it does is it aims to create a kind of pseudo-physical droplet model inside of the solver that will account for near wall air buildup, right? And it'll aim to kind of ventilate that from your hull. In general, it's a combination of getting a good quality mesh in that area, because it's, numerical ventilation is mainly driven by smearing of that interface, and so the focus needs to be on maintaining a high quality interface. And so a lot of the work that I did, the VOS slip model helped a lot, but you've also got to rely on having good mesh quality and getting a really robust mesh. But in general, a lot of the work we do, especially with RaceBird, is high speed craft, and we use Star CCM for all of that. So definitely able to handle it. Obviously need to be a bit careful with how you mesh things to avoid those ventilation issues.
Yeah. Perfect, thank you. I haven't seen any other questions in the section, so maybe wait a few seconds if somebody's got a last minute one. Otherwise, I'll start wrapping up, and first thanking you all for attending today and being with us today. There will be a recording available online, so I know there was a lot to take on at some point, so if you want to have a look at the recording, do not hesitate, and if you want to contact us, please feel free to reach out to us by email. And yeah, obviously, save the date of the 26th of November. There will be that hands-on event in London. So thank you very much, and have a good rest of the day.